One more time, good afternoon, dear colleagues. Today we have guest speaker Oleh Ryzhov from Poznań University from Poland, and he gave us a talk about spectroscopic search of dual active galactic nuclei. Please, Oleh, welcome.
Yeah. Hello, everyone. My name is Oleh, as it was presented. So I'm from Mickiewicz University, Poznań, Poland, and today I'd like to present you our new project I am a PI of. So here you can see the list of my, let's say, colleagues, teammates that I'm working with. So yeah, today we'll talk about dual active galactic nuclei. So the talk will be strictly extragalactical. So we'll talk about extragalactic astronomy. I know that many of you do different things like asteroids, minor planets, and so on. But overall, the talk is rather statistical. So I do statistical research. That's why your expertise might be also in different statistical or mathematical things might be useful. So please stay tuned and let's go with the introduction. Okay, I will start with a little organizational announcement while I hope I still have your full attention. So I am a participant of Extragalactic Team of Poznań. We have a couple of members, and you can see the photo over here. And the thing is that we have announced a PhD position for the 4 years, and the deadline is in a couple of days. So in case you or your friends or students are close to receive their master or already received their masters and didn't enroll to PhD studies, they can apply. And of course, if they are interested in extragalactic astronomy, so you can see here the list of our interests. Yeah, we do mostly ISM. We also study supernovas. But yeah, basically ISM and everything what is connected to it. And we actually love dust. So everything about dust production, destruction, observation of the dust. Also might be probably interesting for the students that do radio observations from the Radio Institute of Kharkiv. We also are interested in such people. So please, if you're interested, scan the QR code or send the link to your friends and apply to us. And yeah, we are quite ambitious. We have a couple of grants, scholarships, and for the last year we published 5 papers in highly widely known journals, as you can see them at the slide. So yeah, that's pretty it about organizational announcements. And now let's switch to science. Okay, so I will briefly present to you what are dual AGNs and actually why we should care about them. Okay, so let's start with some basics. So let's talk about galaxy mergers. We know that these are extreme phenomena. So just imagine 2 galaxies with a lot of interstellar medium, stars, they collide with each other. There are a lot of different things going on. We know that there can be starbursts caused by mergers. We know that cohesion can be caused by the merger of 2 galaxies. Also, nuclear activity. We know that the brightest quasars in the universe are rather connected to mergers, rather caused by mergers. So very interesting to simulate them individually, and we don't really know a lot about, let's say, the overall statistics of merger, how they happened with the evolution of the universe, and how they actually affect the evolution of galaxies, let's say on the larger scales, on the larger samples. So it's very interesting to study. And we actually know that merger happen. It's not some unique and extreme phenomena. It's rather common for galaxies to merge because the galaxies at the current epoch, they have so high stellar masses that actually no star formation can explain that. So we know that galaxies should have merged. So extreme processes, a lot of different physical phenomena is sitting inside there. A lot of different time scales is sitting inside there. And we know that all that happens and is related to almost every galaxy in our universe. And of course, if these are extreme processes, they produce extreme objects. So we know that luminous infrared galaxies and ultraluminous infrared galaxies are rather connected with mergers or galaxy interactions. Submillimeter galaxies and starburst galaxies also, it happens to be mergers. Okay, but I was sitting at some day and thinking, but okay, we have galaxies as we can see here at the simulation. And my general question was, what happens to the supermassive black holes inside them? Because we know that supermassive black holes are inside galaxies, are in the centers of galaxies. So what happens to them in the merge? And that's why I started to read the literature. I started all to research, and it turned out that, yeah, one of the possible, I'm not saying that it is in every merger we see something like that. No, one of the possible merger outcome is dual active galactic nuclei. So imagine you have two galaxies with two supermassive black holes inside them, and they slowly, of course, merge with each other. But then all the matter, let's say, forms new galaxy. But inside this galaxy, you have two supermassive black holes, which usually are going into active phase. So they turn to AGN phase. They become active galactic nuclei, and they also start to rotate around each other at kiloparsec scales. And they then slowly decay their orbit. Finally, they become binary black hole system, and then black holes coalescence, and they form new, bigger black hole, let's say. So yeah, you can read the perfect paper by De Rosa for the review of all these phenomena. Okay, so that's pretty it. I guess you already got the idea of what is going on here. The thing is, why do we care about that? And the point is that we know that AGNs by themselves are powerful sources of feedback. We know that they provide a lot of ionization, heating processes. They produce a lot of turbulence things, magnetic fields, outflows, jets, a lot of different things that can actually shape galactic evolution. But imagine that you have not one AGN, but two AGNs that rotate inside the galaxy. And then the question is how all these phenomena actually affects the galaxy evolution. What is the feedback from dual AGN? What can we say about activity and variability of these AGNs? What is going on between these nuclei? That's very interesting. And there are a bunch of different other questions. I can list them till the end of the lecture, actually, to the end of the presentation, but I don't want to do that. Anyway, there are too many things, too many questions, too many uncertainties, and there are not so many answers. So yeah, if you're interested, please join us and we can explore them together. Yeah, anyway, then the question is how we can find them. Why we do not know almost, well, not nothing, but not really a lot about dual AGNs. Well, the point is that it's tricky to select them. So we know that mergers are common in sense of evolutionary stage. But if you look at the sky, you will see, okay, one merger for 10,000 of objects, for 100,000. It's we actually cannot list the number here. It's also very tricky. It depends. So you need, but overall, you need to gather a lot of data, and you need somehow to process a lot of data in some, let's say, physically available period of time. Okay, not in the hundreds of years or so. That's the thing. So you can see, like, look here at the plot, and you can see overall, well, you can see the redshift and more or less this, well, it's separation between dual AGNs, but you can see that we do not have really a lot of them. Okay, there is the study by Liu plus Liu et al. 2011. I would not really trust all these gray points, the cloud of gray points over here. There were no follow-ups for this, as I remember correctly, so I would be rather conservative about this cloud. So you can just look from the redshift 0.2 to the redshift 3. You can see that we have hundreds of confirmed duals. So we don't actually have a lot of them. That's very interesting. So we need to gather these phenomena to study them, let's say, from the statistical point of view. Okay, so how we can actually pre-select, let's say, dual AGNs? First of all, we can, of course, use imaging data. So you can just, well, it sounds very simple, but in fact, it's not. You can search for optical images for double and triple sources with, let's say, extragalactic redshifts, with extragalactic photometric redshifts. Yeah, of course, you will select gravitational lenses. And as I was told, there is a person in here that does such a research. So yeah, that's one of the thing, and people do that, and people publish paper about that. So yeah, that's one of the things. So yeah, here you can see at the image more or less examples of gravitational lenses like these Hubble crosses. I don't remember the correct term for that, and also just 2 points to dual AGNs in here. Yeah, another thing what you can use, it's more simple, but still it's tricky, it's spectroscopy. So you can just look into emission lines of the galaxies, and usually what you see in galaxies is you see just simple Gaussian profiles and lines. Like if you look at the image over here, I hope you see my cursor. So you can see that like, okay, there is one line and another line, and they are constructed from one simple Gaussian. But if you look at the top panel over here, you can see that, okay, we have something more complex. You cannot explain these lines with only one Gaussian, you need something else. So you can see that there are two peaks, they are more or less at the same distance. So now the question is, what causes this duality? So we call these double lines features 003 emitters because these lines are O3 lines, the famous lines of any active galaxy. They are present in AGNs and star-forming galaxies. Well, mostly people talk about AGNs when we are referring to O3, but usually they forget that they also star-forming galaxy emit this line. You can use other lines. I know papers when people use neon and ferrum lines, some coronal lines to tell something about duality, to pre-select dual AGN candidates. But yeah, basically the strategy is simple. You just look in the spectra. If you see some duality there, probably it's dual AGN, but it's not the 100% chance that it's dual AGN. Also, there are different other things, like people use mid-infrared colors to select dual AGNs. I don't know the physical sense of that, but okay, fine. People publish papers about that. Okay, let them do their science. Yeah, also you can, of course, then after you pre-select your sources, you need to have some follow-ups to actually confirm. Nobody will observe with ALMA, the patch of the sky of 10,000 square degrees to select dual AGNs. Now, you need firstly to pre-select your sources and then use some expensive facilities to observe them. So yeah, there are a bunch of different things. People use X-ray observations, radio, as I said, sub-millimeter. Our team is in love with ALMA, so we wanted actually to send proposal for this cycle, but we didn't have too much time to do that. So yeah, here at the image you can see the optical images from HSC. I don't know, it's not HST, it's some other program. And you can see the ALMA contours, ALMA CO observations. So you can see still that in molecular gas, in CO lines, we still see this duality. We still see this dual structure. Good. So yeah, as I mentioned about spectroscopy, what about this 003? It's very easy because you just process one-dimensional data. You have on x-axis, you have the wavelengths, on y-axis, you have the flux. It's very simple. Then you just, you need to fit the continuum, and then you need to extract Gaussians to play with Gaussians. So it's easy, but the problem is that this duality in O3, it can be caused by different scenarios. So dual AGNs, of course, rather have this duality in O3, but also jet can cause such a duality. Outflows, of course, if we have just two star-forming galaxies that are merging and there is some dynamics of excited gas, it can also produce O3, such a double profile of O3. Finally, disk rotation. If you have some very symmetrical O3 and the separation between these peaks is not so high, probably it's disk rotation. I would not say that we see accretion disks at, let's say, redshift 0.2 with our instruments. Maybe with some very good IFU, you would see that. I work with single aperture spectroscopy, so rather not. But anyway, any complex dynamics of gas and kinematics of gas around AGN can cause such duality. So it's tricky. It's very, very tricky to use such things. You cannot blindly say that, okay, every 003 emitter is dual AGN. No, you need to do some further analysis of that to prove that indeed it is dual AGN. Okay. So firstly, what we needed to do, we needed to write some simple spectroscopic tool actually to pre-select our 003 emitters and probably dual AGN candidates. And it's pretty simple. I still consider this tool, that's my tool. So I called it DAIQUIRI from Dual AGN Intelligent Query. So yeah, as every astronomer, I love acronyms. Anyway, it's pretty simple. You just need to retrieve the spectra. You need to feed the continuum. And then you need to play with these peaks because we know that dual AGNs rather have these narrow, they produce these narrow Gaussian components because we have these narrow line regions and so on. Anyway, we expect there to have some peaks. We expect peaks in the spectra. So yeah, we need to play with the peaks. As soon as these two lines, two O3 lines, are of the similar nature, we expect same positioning and same heights of peaks. Well, I mean, not same heights, but the ratio of heights should be more or less the same. And yeah, then if everything is fine, I apply advanced Gaussian modeling and I check if indeed duality is statistically, let's say, significant. So I check Bayesian information criteria. So if we increase degree of freedom, basically, is it really worthy? Do we get really higher, not higher, but lower residuals, statistically lower residuals? So yeah, if you know what's Bayesian information criteria, that's probably, you got what I mean. But yeah, basically we need to check if duality is indeed better than dual AGN, dual Gaussian is indeed better than single Gaussian. Okay. Yeah, and from 1 million of galaxies that we processed till the redshift 0.6 with this tool, we already have 300 003 emitters, and I applied quite strong masks. So in reality, there can be even more. So we chose only the strongest with highest signal to noise in all three lines even available. So yeah, we have already 300 of objects that we can actually play with. So now, yeah, before I will tell you what data do I use, and then we will switch to results. Okay, so we need some massive spectroscopic surveys. One of them is GAMA, Galaxy Mass Assembly. It's an Australian survey. I would not go deeply into all these technical things. The point is that they gathered for 12 years of their work, they gathered 300,000 galaxies with all the photometry and spectroscopy done, plus a lot of different value-added catalogs. So it is very useful thing if you want to study local universe, let's say till the redshift 1, and you don't want to have a problem with really big data. So I think all the catalogs there are less than 1 gigabyte, so it's still achievable on laptops. Something else is DESI. So it's actually nobody in Europe, at least I have the feeling that nobody in Europe knows about this survey. I heard of it at one recent conference, which involved American guys. So it's an American survey done. I think the telescope is placed somewhere in Arizona. Anyway, they go deeper, they go wider, and for 1 year of their work, they collected, let's say, 10 times more, even more, 20 times more galaxies than GAMA did for 12 years. So the technology jump is insane. So we have already 14 million galaxies in data release 1 with all the photometry and spectroscopy done. It's enormous amount of data. Like, I should be honest with you, we haven't processed them all. We processed only the part of this 14 million. So it can turn out that we will have more dual AGNs, I mean 003 emitters, and then hence consequently we will have more dual AGNs in our sample. So if you want, they also gathered spectra of stars. So if you're interested in stellar spectra, if you're interested in extragalactic spectra, if you want to do some cosmology, to actually play with the dark energy and dark matter, please check out the survey. That might be very useful for you. Okay, so what are the first results of my project? Yeah, as I told, it's the DAIQUIRI project. Okay, so first of all, let me just show you some simple statistics for these 311,003 emitters. Here you can see the distribution of redshifts and distribution of offset velocities, so velocities between these O3 peaks. You probably I would not probably explain to you how we calculated that. It's very simple Doppler shifts and so on. Anyway, we see that, okay, we have the peak velocity at, let's say, 250, 200 kilometers per second, which is okay. Every study of dual AGNs, of 003 meters and dual AGNs usually tell us that. So yeah, when people process these O3 lines, that's the usual thing that what they get is something like that. But we have a couple of galaxies with really high velocity separations. I think we have like 5 of galaxies with the velocity offset of more than 1,000 kilometers per second. It's a very good result. We definitely need to study them deeper because people usually do not find such a galaxies. And we have one really offset guy with the velocity separation of 2,300 kilometers per second. So something interesting to check out. With Redshift, everything is fine. We want to go further in Redshift to trespass the 0.6 limit because, yeah, we are limited because of the O3 line. After that, the O3 line is shifted to already infrared, and we don't have any constraint on what is going on there. So yeah, that's the thing. Okay, then we of course need to check how our tool actually fitted the spectra continuum, if indeed there is some duality or not. And our mask works really well. We have only 2 galaxies with bad data. I call these galaxies wavies. You can see such spectra of such a galaxy actually at the image. It's not something physical and natural. It is something which is caused, I guess, it is instrumental effect. I don't know, it's some interferometry, the signal from the spectrograph. Yeah, I think that's the explanation. So yeah, something instrumental is going on there. This is the bad data. We want to remove it, but it's tricky actually to remove such galaxies from the sample because there is no flag that actually can that we can use in the catalog to remove such galaxies. We need to write some algorithms to do that. So yeah, that's why the continuum fit of the DAIQUIRI is so complex. I haven't mentioned yet that, but yeah, it's very complex algorithms to fit the continuum, and it's not really ideal, I would say. Another thing, what we have there is like 10 galaxies. We indeed see the duality. The DAIQUIRI worked well, but when I look at the spectra, I think it's telluric lines that went there. So we have some emission lines from the sky, and they are quite close and massive. So yeah, basically, this is also not bad data, but it's not AGNs which caused the duality. It's the sky that caused it. So we also remove these galaxies out of the sample. Good. Next, we check not only spectra, but we also check images. So yeah, basically, it's when I have some boring humanity class, I just turn on my laptop and I check SIMBAT. And I had a couple of classes like that. So I already processed all the sample. We have 17 confirmed mergers or galaxies that are in clusters. So indeed, there is some some gravitational interaction. And there are like 130 sources. I see that there is something going on, but nobody actually measured the spectra, nothing, only DESI did that. So we don't know what's going on there. Yeah, so, and something like 160, there is nothing really interesting. So yeah, that's basically the thing. So we don't actually have a lot of mergers in our sample, but indeed we have a lot of these 003 meters. Who knows? Maybe I do not see, well, my explanation is that I do not see a lot of late type mergers. I cannot tell if it is late type merger or it is some just single non-interesting galaxy, especially at redshift, let's say 0.5. So yeah, it is some kind of analysis, but yeah, you should not really look into that. Yeah, and also we search for some counterparts in radio, in X-ray. So yeah, we have 17 LOFAR detections, 25 VLSS detection, 1 X-ray detection from Rosita. Why did they leave here the question marks? You might ask me this question. The point is that we haven't done that yet. It's in the plan. We don't know what galaxies were observed and not detected, and what galaxies were not observed by this instrument. So we need to do these statistics to get, let's say, the fraction of the real fraction of detections. Yeah, and one of the most interesting is that we have X-shaped radio dual AGN. So yeah, actually it was listed in some paper. So yeah, here you can see the image, the optical image on the background, and some radio counterparts with this that are emphasized with these contours. So yeah, you can see that there is double radio nuclei, which is very interesting over here. And we have probably we have jets, but their structure is somewhat, as you can see, symmetrical, and it has something like X shape. So it's a very interesting case. It was studied by Sebastian, but it was purely studied by radio, as I remember. So we want to look into it with other instruments, for example, ALMA, to see what is going on with molecular gas inside there. So indeed, we have a couple of interesting cases from radio detections. I will just check out the time. Oh yeah, I already took quite a lot of time. Good. So yeah, then what you also can do, you can estimate the star formation rate from radio signal and star formation rate from H alpha. And what we see here at the plot, it's quite preliminary plot. It's some pilot study, let's say, no uncertainties, nothing. But rather all the sources that have H alpha detected and radio, they are definitely AGN. No star formation can actually explain the radio signal that we see. So yeah, indeed, we have some AGNs, probably jets, who knows? Yeah, also what you can do, you can go deeply into spectroscopy, more deeper into spectroscopy. So you can feed different combinations of Gaussian functions to H alpha and H beta complex. So you can get the lines like H alpha line and 2 line over here and so on. Why do we really need that? Yeah, of course, we need to estimate uncertainties and fluxes. Our point is that we want to do the emission line analysis of separate components. So the point is, okay, we have some, let's say, red shifted blue component and blue shifted component. The point is that we actually don't know from the O3 line what is the nature, what is going on inside there. If it is something connected with AGN or it is something connected with star formation, it can also happen. So we do this BPT statistics. It's very famous in extragalactic astronomy. So basically you just take the fluxes of O3 line of separate components of in O3 and H beta and 2 and H alpha, and you plot it. And what you can see here is blue wings and red wings connected with these dotted gray lines over here. And you can see that, okay, for example, let's say this galaxy, this case, it is something connected with star formation. So it's definitely not AGN, which, let's say, produces these lines. It's very broadly speaking, but okay. And this galaxy, for example, 2 components have AGN nature, something to do with AGN. So we do such a, yeah, here is just the visualization of 10 galaxies. Of course, I do not plot, I do not look at the image. I just put the algorithm and then I produce statistics. It's quite an old result, but it more or less shows the trend. So only 1/3 of actually selected 003 emitters are something to do with AGNs. Okay, here it's 40, but more or less you got the percent. So we cannot definitely say that each 003 emitter is probably dual AGN. No. Maybe it's just the merge of 2 star-forming galaxies, or rotation of star-forming disk, or something else is going on. Or we have the clump of star formation in the galaxy. Nobody knows, but the point is that, yeah, only 40% of the galaxies, of the selected galaxies, are something to do with AGN nature. And we still have jets, outflows, some complex kinematics of gas around AGN, and so on. So yeah, another interesting statistics, it's old one, but also it shows it's interesting in terms of velocity separation and spectral classes. We see that star-forming classes tend to have something like less than 200 kilometers per second. And AGNs rather go, like the fraction of AGN increases with the increase of velocity offset. So we can see it over here. The blue columns slowly increase. We do not look into everything which is higher from 600 kilometers per second, because you can see there are only 3 galaxies in the beam, or 1. So yeah, that's basically the thing. Very interesting result. It's already something to publish. Nobody did that before. Also, what you can do is you can calculate the distance between black holes. So for that, you need to estimate the masses of black holes. So yeah, you can just apply the usual formula that we all know from the course of celestial mechanics, or just from the school. So yeah, you can just estimate the black hole mass using the stellar velocity dispersion. So this sigma, probably many people know this relation as sigma mass black hole mass relation. So you can just estimate masses. Well, the tricky point in the formula is the orientation angle, so how your orbit is oriented towards the observer. We just assume something like 0.5 because we don't know actually how our AGN is placed towards the observer. And delta V we estimate from the O3 line, so basically the distance between the peaks. And with all that, you can actually get the distance, the D over here. So that would be the distance between your black holes, or some kind of estimations of it. And here at the plot, you can see the distance on the x-axis and the number of galaxies on the y-axis. You can see that most of our galaxies, well, not the most, but let's say 70 galaxies from 300 have indeed separations less than 5 kiloparsecs. And then something interesting is going on. I would say that everything above 20 kiloparsecs, it's something to throw away. So it's not dual AGN for sure, even though it can be AGNs. So we have another test to apply. So everything which is, let's say, closed in this segment from 0 to 20 kiloparsec, that's something to study deeper. So yeah, that's one of the things. The point is that I don't really trust the masses of black holes now. It's very recent result. So you can see here at the plot that, okay, we have the stellar masses over here. We have the black hole masses at the y-axis. And you can see that some of our galaxies have black hole masses higher from stellar masses. I suppose that it is something to do with the stellar mass estimation. Something is wrong, or something is wrong with the black hole mass. We cannot, for some reason, apply the black hole mass estimations with the sigma to our galaxies. It got tricky. I don't know. It's very fresh result. I did it like this weekend. So it's still something to analyze. So we will see how it goes. Yeah, so our next point is we want to study physical properties of our galaxies, and we want to compare dual AGNs to single AGNs. How all that evolves, what are signal to noise ratios, how all that depends on that. So yeah, it's all the projects now. I thought that it will be just very short publication, and yeah, my master's thesis, but now it got really giant and very ambitious. We have a lot of different to-dos in the close future, starting from just running all the available spectroscopy for galaxies from DESI. Also, we have the Euclid survey, to all these physical properties. And yeah, we wanted to submit ALMA proposal for this cycle. So the deadline is, I guess, this Thursday. But no, we didn't. We had so much to do. So we didn't do that. So we will probably apply for the next cycle with ALMA. Yeah, if you're interested, please find me. You have the email over here. I'm present at Google Scholar and NASA EDS. So you may find my email, my contact data. Good. So I will leave you with takeaway. I remind about the PhD position of our team. So please, if you know some people, if you are a person who is interested in extragalactic astronomy and you just finished or you're finishing your master, please apply. And yeah, you have the QR code. And I guess that's it from my side. Thank you. Yeah. Oh, my camera is. Okay. So yeah, if you have some questions, I would be happy to answer them. Yeah, because I think I was quite fast with the presentation.
Okay, thank you very much. Please, questions from audience. I have one simple question.
Okay.
You told us that your team deal pretty much with DESI data.
Yeah.
But we know that, for example, as DSS project also obtain spectra of galaxies.
Yes.
And you try to compare data for your candidates in double AGN between SDSS and DAISY. There is some
Okay.
interception.
Yeah, there are some, let's say, yeah, that's something to do. We also want to do that because we don't want to publish one more time. Well, DESI is better spectroscopy. DESI has better spectroscopy. DESI has better signal to noises. But anyway, DESI fields are covering as DSS fields, so we would expect to have galaxies that have detection, that have duality detection in SDSS, they must appear in DESI. So it's something to do. We already had such thing with GAMA. So there were a couple of double observations. So we had the observations from GAMA, we had the observations from DESI, and both of them showed that duality, but I kept only one because it's like one galaxy, not to include two similar galaxies, let's say to the same galaxies. So yeah, it's something to do. But yeah, you're right. It's I want also to test the DAIQUIRI and already known spectra. So I will take spectra from SDSS because there are a bunch of publications about searching of dual AGNs and 003 emitters in SDSS. Nobody for some reason used GAMA, and nobody yet used DESI for that. So yeah, that's why we do not use SDSS, for example. So yeah, that's the thing. But yeah, it's in the plan.
Okay, thank you. Please, other questions?
I have one question. What is? Oh, do you hear me? Sorry.
Yeah. I hear you. Yes.
Okay. What is the typical angular distance between AGNs in your sample? And is it possible to see on just optical images as a double or something like this? Because you show some double quasars and other in beginning. Is it possible to resolve it in optical range?
The point is that, well, yes, if it is at really low redshift, we indeed see some mergers over here. Like here is the perfect image, probably, where I see that, okay, there are two galaxies, two nuclei over here. Well, the angular distance over here is like 3 arc seconds or so. Well, the typical angular distances, well, they are different and different, let's say, redshifts. The physical is usually something about like in the range of kiloparsecs from 1 to 20. You have seen that estimations. So yeah, it might be 1 arc second, it might be more than 10 arc seconds, and then if it is 10 arc second, no, we will not see that if I see that the galaxy has 10 arc seconds, and the distance between black holes is 10 arc seconds, and I see that my galaxy is like 3 arc seconds wide, no, it's not dual AGN for sure, and there is no other. So it's something else. But yeah, typically it's sub-arc, like something like arc second or less. I would say.
Okay, and in this key, did you try to use Gaia data, for example, for that have a
Oh.
very high resolution,
Mm-hmm.
to find binaries with spectral, with a, yeah.
In fact, somebody did that. I think it's Manucci who did that. I've showed you that publication. So if you're interested, you can check out. I don't remember exactly. I think they firstly did some Gaia observations.
Yeah,
Oh,
because
my
Gaia
presentation.
cover all the sky, and DAISY have also a big area.
Yeah,
Therefore,
yeah. So I think Manucci did that already, or I've seen some publication that's already processed Gaia
but it
data.
was before DAISY, because DAISY release was in this year, or maybe
Yeah.
last year. Yeah.
But DESI, well, DESI is rather spectroscopy. There are some photometric measurements, but DESI is rather oriented to spectroscopy. Well, if there are some photometric data, I would happy to get that and to use that and to study also that. But yeah, if you're talking about really high resolutions, Gaia already, I think, is covered. There are a bunch of papers about Gaia.
It could be
And
like a preselection criteria, for example, binaries that have a spectroscopy as a quasar or AGN from DAISY. So binaries from Gaia,
yeah.
and you can,
hmm Yeah, that would be actually interesting to do. Like, but I think for such sources, they do the follow-ups. So they do all the VLT observations or Hubble observations, and they get the spectra in these papers. So they know exactly the redshift. So yeah, you can see it over here, actually. So they know the redshift of these sources that they selected, let's say, from imaging. So yeah, but indeed it might be actually interesting. I was thinking about another project to use LSST data, which we hope all probably will have the first light this year, because it will be a lot of high resolution images with really good coverage in sense of magnitudes, and actually to look there for dual AGNs, and but taking into account the amount of data. And
sorry, why LSST? What is the improvement of LSST? Because it's have the same optical resolution, like 1 arc second, maybe
because
less.
of the seeing, right? Yeah.
And it's,
But we will go deeper, for example, in sense of magnitudes. I would say
yeah,
that, for
but you
example.
need spectral to
And that's where we would,
recognize.
and
Yeah,
that's where
and
we will probably go into DESI. So we will search for LSST plus DESI, like we will get the fields from DESI and we will search for LSST data there. And maybe we'll see if we see something that is covered by DESI and LSST and there is some duality in LSST, like
no,
something like that. I was
LSST
like,
maybe,
nah.
sorry, LSST
Mhm.
maybe it's not a very good. Euclid, yes. If you use Euclid as a high resolution and spectra from DAISY,
Mhm.
so you get a good condition to selection, but not LSST. On this.
Okay. Okay. Well, that was just, I'm thinking about like where to go with this project. Indeed, I want to go also in Euclid, but I think they have done the spectra. It's the spectroscopic survey, if I'm correct. I don't remember.
No, no,
But
no,
yeah,
no.
anyway, I
It have
want to also
just
to go.
high resolution images, so and infrared
Yeah.
also, but it's not enough.
Uh, that's why I'm interested in Euclid because it's infrared survey. Wait. My presentation is lagged. But anyway, we want to go higher in redshifts, as I mentioned. Euclid covered every infrared, like it did infrared spectra. So we would see all these O3 lines that are shifted to infrared. So redshift, let's say 1 in Euclid, and we will get some statistics. So yeah, that's another thing that we want to do, to run the Euclid data. So yeah, there are a lot of things that can be done. I think we will come to Imogen at some moment of the project, not now. Now we want to finish this big
Yeah.
spectroscopy part, and then we'll switch to Imogen
And
probably.
one little question: why
Yes.
O3 lines it's higher or narrow? Uh,
Um, Well, it is about AGN, let's say regions around AGN. So we know that AGNs with their emission, well, with their excitation, they produce different regions. We know that there are broad line regions, let's say coronal line regions, and there is also narrow line region. And these narrow line regions, they usually have low velocity dispersions, so they are indeed narrow. And they are not connected actually with some rotation around AGN, so you cannot use them to, for example, estimate your black hole masses. That's why I play with this stellar dispersion. But anyway, it's off topic. So they are narrow, they are very strong. We see that in the spectra. So yeah, basically, we do not actually trace nuclei with O3. We trace these narrow line regions. That's why I said that it is complex, because we do not trace AGNs, like the nuclei. We trace the regions around them. So it can be like one single AGN, but just with some mesh up in the kinematics of gas around it. We observe that, we see that, and we state, okay, it's 003 emitter, then we need something else to do to study like if it is dual AGN or not. So that's the thing. Yeah. So still there are a lot of uncertainties.
Yeah,
Yeah,
I
but
understand. And can be splitting these narrow lines will be a result of maybe rotating inside one black hole or just a clouds around.
yeah.
So,
I
but
mentioned that. So yeah,
yeah,
the duality can be caused even by disk rotation of the galaxy.
yeah,
It will not be at so high speeds, like 1,000 kilometers per second, no, but 200 kilometers per second rotational, like the rotation of the galactic disk, or I don't know, some, yeah. So basically, it can be just the cloud of ionized gas that, for some reason, we have it like as a clump, and that's why we see such a spectra. So yeah, there are a lot of, it is very difficult to study that with just pure single aperture spectroscopy. I would love to study that with IFU, but I don't have so many IFUs. That's something also to do.
Okay,
Yeah.
thank
Yeah,
you.
but thank you for the questions. Yeah. It's good that people know also about Euclid. It's nice to hear. Good. I will
More
stop
questions?
because my presentation.
There is some other questions?
Yeah, I would happy to see some questions from students also, like even some, if you consider that as a stupid question, no question is a stupid. No, please go on. I would be happy to answer.
I have one small question.
Yeah.
Do you try to search some of interesting objects in your sample on Hubble data?
Good question. Not yet, but it is in the to-do list also to search for JWST data.
Yeah.
I think we will not have a lot, but maybe we'll have some, because Hubble and JWST, they do not have so big fields. Well, Hubble maybe for 30 years it has some of the field coverage, but not JWST. But we want to do something else. We want to take JWST spectra and to look there for duality. That's also another project that we started to do. And then yeah, we will have JWST imaging and spectra probably, because usually first it's JWST imaging and then spectra. Yeah, so yeah, it's in the plan to look for Chandra also data. Maybe we might be lucky to get it. One more time, all these surveys are very, very, let's say, small in sense of field coverage. They're very narrow field. So not surveys, telescopes.
Your object not large. They are also small, and probably there was an object of interest in some different projects.
Yeah. Also, like while I was preparing, let's say, ALMA proposal, I found that, for example, one of my galaxies of the most interesting galaxies was observed by ALMA previously. Unfortunately, with not really good resolution, not the resolution I want with, let's say, 1.8 arc seconds or so. I want less with ALMA, but yeah, it might turn out like our objects are interesting and maybe they were already suggested and observed. So yeah, also in the plan to check that out, and it would be a lot of the thing to do, like to check all these facilities and their data.
Okay.
Insane. Yeah.
Thank you. Some other questions? If no, let's thank our speaker again. Thank you very much, Oleh.
Yeah.
And we probably want to have your talk 1 year after this time.
Yeah, I will
result.
be happy to give out, yeah, maybe already with the published paper.
Mhm.
Okay.
Okay.
Yeah, thank you very
much.
much for your attention, and